Sir is here.
Muted. Am I audible now?
Yes, sir. Yes, sir. You're audible.
My apologies for the delay. Yeah,
No problem.
Let's begin right away.
Yeah, just a second, sir.
Yeah.
Yeah.
Good afternoon to one and all present here. Today, the Department of Msc Big Data Analytics, along with IT and BVoc SD, presents a webinar on the topic, what is research and what is the importance of it in the field of IT. So, Niharika, what exactly is research?
Research is a process of systematic inquiry that entails collection of data, documentation of critical information, analysis and interpretation of that information in accordance with suitable methodologies set by specific professional fields and academic disciplines. But Chahana, why exactly is research important in every field?
So, not only is research an invaluable tool for building on crucial knowledge, it's also the most reliable way we can begin to understand the complexities of various issues, to maintain our integrity as we disapprove lies and uphold important truths. John Armstrong, a respected global higher education and research professional, once said, aside from the pure pursuit of knowledge for its own sake, research is linked to problem solving. Ultimately, research is nothing but a catalyst for solving complex issues.
No doubt, research is very important. And to shed more light on this, we have Dr. Uday Khedkar sir with us today. He is a professor in the Department of Computer Science and Engineering, IIT Bombay. And he has done his PhD in computer science and engineering with a thesis on a generalized theory of bit vector data flow analysis.
Before we call Dr. Uday sir, we would like to call upon our HOD, Mr. Wilson Rao sir. He is the HOD of Msc Big Data Analytics, BSc IT and BVoc SD. Sir, we request you to please say a few words before we begin.
So my few words would be thank you, sir, Uday Khedkar sir, for accepting the invitation because he was so busy. In fact, his dates were all full up to 8th and 10th of March. But I said that, by the time it would be a little late and you will be all in the exam mode that time. So he has consented today's date, and we really wanted him to speak on the topic of research because we wanted not just you all, but even the faculties to know mainly about the research because he is into this field. In 2011, I had invited him on the same topic. Basically, we had an international conference that time, and he was in person present in Jai Hind College. And by God's grace, in 2021, now we want the same kind of concept because the young minds, and especially we started MSc, have to be guided in the proper manner of what is research and how to start about this research so that they are being knowing this field properly and can do their job properly. So Uday Khedkar sir, a big thank you to you. And without taking much time, I invite you to start your session.
Sure. So I will open up my slides and share the screen. Is my screen visible?
Yes, sir.
Is it any better now?
Yeah, it's better now.
Okay. So first of all, very warm good morning to all of you. It's always a pleasure to discuss something that's been very close to my heart for a very long time. As Wilson sir said, yes, things have been a bit hectic and somehow I managed to find time today. But again, there's some delay and my apologies for the delay. So I'm going to take up the main question that was raised in the beginning by Niharika or Shahna, whatever I missed the name. What is research? And I'm going to I'm going to spend all the time on this particular topic. What is research? Uh, I would like you to keep asking me lots of questions. I hope there is a coordinator who can draw my attention to raised hands, or who can draw my attention to questions if you ask in the chat. I would rather want this to be a dialogue. I don't want to be a monologue. Feel free to ask me questions at any point of time. Secondly, this talk has lots and lots of material. I might dynamically decide to skip some material to keep time in mind. Uh, we said that it will be about 1.5 hours, so it's about quarter past 3. So I hope, I would definitely like to finish by quarter to 5. Certainly won't go beyond that. It's my promise that I won't engage you any more than that. Okay, so here is an outline of my talk. We'll begin by asking the question, first of all, why should we do research? And then we'll talk about what is research. And then we'll talk about where do good ideas come from. Then we'll talk about the process of research. And then I'll touch upon a very interesting talk by Richard Hamming on research. This talk is titled "You and Your Research," and its transcript is available on internet. I very strongly recommend that you look at this talk. It's one of the most influential talks on research that I have come across. And finally, we will conclude. Some disclaimers are in order. Uh, Here I will talk about some general concepts. This is not a cookbook or how to do it yourself manual. I have no such illusion that at the end of this talk, everyone will immediately start doing a wonderful research. No such thing is going to happen. What's going to practically happen is uh, I will perhaps succeed in sensitizing you to what research means, what people do when they do research, and more importantly, why do some people like us get hooked to research, and why we find research very fulfilling. That is the main motivation behind this talk. So this is an attempt to explicate what most researchers implicitly believe and may not articulate. And these are views expressed through examples. And this is an individual's perspective rather than an organization's perspective. And more importantly, these are personal reflections and confessions. Confessions, because I recall when I started developing this talk, I recall facing some difficult situations in social settings and family gatherings. There would be conversations like, "Okay, so what do you do?" So I would tell them I teach. So they say, "Okay, how much do you have to teach?" So I tell them that at IIT, we teach typically one course a semester. So then they ask, what does it mean to teach one course a semester? So I said, there are 3 lectures a week. Then they ask, okay, what is the duration of one lecture? So I would say it's typically 1 hour per lecture. So they said, oh, you work for 3 hours a week. That's such a nice life that you lead. You have to work only for 3 hours a week. And then I had to struggle trying to find out what do I do in the rest of my time if I teach only for 3 hours a week. So this talk grew out of those personal reflections and investigations and introspections. So let's begin by looking at what is research. Here is a picture that I have, and this picture is from uh, the book Through the Looking Glass. It's about Alice's wonders, adventures, and I'm sure all of you have seen this picture. It would have been nice if we had some interaction. Would someone like to unmute and tell me what does this picture show? Someone? just maybe a few seconds.
You can raise your hand and we will unmute you.
Yeah, somebody
Good.
please. I just want it to be interactive, so
Yeah.
just to break the monotony.
Yep.
Please feel free to express your opinion. I am at least 15 kilometers away from you physically to punish you. So do not worry about expressing your opinion. Would anyone like to say something? Okay, let me not spend much time. Let's proceed. So this is Lewis Carroll's book Through the Looking Glass, and this picture shows, if you can see here, this is little Alice. She is holding the hand of Red Queen. This is a Red Queen, although the picture is black and white. So she appears black and white. This is the Queen's staff that she's holding in her hand. And Alice is running, holding the hand of the Queen. And they're running very, very fast. And they're running so fast that the Alice is panting with the effort of running. And then Alice makes an observation. Alice says, well, in our country, said Alice, still panting a little, you would generally get to somewhere else if you ran very fast for a long time, as we have been doing. Oh, a slow sort of country, said the queen. Now, here you see, it takes all the running you can do to keep in the same place. If you want to get somewhere else, you must run at least twice as fast as that. So that's the point. The world that was so fast that even to remain in the same place, you have to try with all your might, otherwise, you'll be left behind. If you want to get somewhere else, you must run at least twice as fast as that. In order to survive in a world of rapidly changing technologies, we need to run twice as fast to remain in the same place. And for that, we need hard skills, we need some soft skills. By hard skills, I mean we need to have technology skills, we need to have technical skills, we should be able to understand technology. For example, we should be able to understand what's happening in this Zoom call. How is it that I am sitting at such a long distance and I'm able to talk to you in real time? We need to have soft skills. We need to have leadership skills. We need to be able to motivate people. We need to have the emotional maturity to sail through setbacks. We need to be able to communicate our ideas. We need to be able to sell our dreams to the people. So these are all soft skills. So all these skills are very, very essential. But in my opinion, there is a third skill which has become much more essential now, and that is the ability to acquire new skills. So whatever skills we acquire, they will be useful, but the trouble is, because this world is changing very rapidly, the skills that you acquire may become outdated very quickly, and therefore we might have to acquire new skills, and therefore the ability to acquire new skills becomes a very, very important skill to remain in this world. And my claim is quick self-learning is enhanced significantly by doing research. So that is our first cut answer. Research helps us to acquire new skills. So why do people do research? So is this the main reason why people do research? So this is not really the main reason, but this is one of the most important reasons. It's good enough for us to get started with this talk, but we'll hopefully have a much better answer by the end of this talk. So having settled or having got a working definition of what we mean by why we do research, let's talk about what research is. So my favorite analogy of research is that of carving statues out of stones. Imagine that you are a sculptor and you are a very good sculptor at it. And maybe you are an expert in carving statues out of stone. So you make one special kind of a sculpture. Maybe you create that huge statue of Gautam Buddha on Hussain Sagar Lake in Hyderabad. So that's the kind of statue that you are expert at in making, and for that you have your own set of skills, you have your own methods, you have your own tools. You might use some chisels, you might use some hammers, you might need a ladder to climb on top of the rock or do whatever else. So you have your own set of tools and methods. Imagine that someday somebody walks up to you and says that, fine, you have been making statues, you have been making sculptures out of stone, but now I want you to do something else. I want you to carve out a statue of Saraswati out of a grain of rice. Let's say that's the situation that comes in front of you. In both the situations, things are same. You are making statues, but in one stage you are making statues out of huge rocks, and in the other case you now have to do something on a grain of rice. So what would you do? You clearly look at your methods and tools, and you'll find that your existing methods and tools perhaps are not really useful. You don't need certainly a hammer, you don't need a chisel, you need a very, very pointed tool, a pin maybe. You need something that can help you hold the rice without breaking it. You need something that will help you magnify the grain of rice. So what that means is that you will attempt to improve methods and tools. So you will try to create new methods, you will try to make new tools, and as a consequence of this attempt to improve methods and tools, this would lead you to be able to make better statues, certainly a larger variety of statues. You will have a better set of methods and tools because now you have more methods and you have more tools. So these are the advantages of attempts to improve the methods and tools. But according to me, these advantages are not the main advantage. The main advantage is that on the whole you have become a better sculptor. You now know one more way of doing something that you didn't know before. When someone else comes up to you and asks for some other kind of a statue, you won't say go back to that person. You will say, wait, hold on, I don't know how to do it, but I'll improvise my methods, I'll create some new tools, and I'll able to make new sculptures. You become a better sculptor. Research makes researcher a much better learner. That's the most important contribution of research. Apart from the advantages of being able to solve the problems, being able to help the society, being able to do something useful, the biggest contribution of research is that research makes a researcher a much better learner. And this is the theme that we will stay through throughout this talk. So, how does research happen? So, there are often observed phenomena with no explanations. There are puzzles and mysteries that need to be solved. Sometimes there are lacunae in the known theory and of practice. Sometimes there's a need of a better understanding or better method. Sometimes there's a need of innovative ideas. Sometimes there are innovative ideas waiting for new applications. All such things happen when people are involved in doing research. And I'll come to an example. Perhaps I think I have on one of the slides. I don't recall right now. I have an example of how we all have GPS on our mobile phone. I think there is something that relates to as to how GPS came into existence, and it falls in this third category, innovative ideas waiting for new applications. So let me move on to research. So what is the essence of research? We've said research makes a researcher a much better learner. We said that, but we still haven't said what is research. That definition still remains unanswered. So I have some questions. It would have been nice if I were to be using Moodle. I would have been able to do a quick Moodle poll here in Big Blue Button, asking your opinions. But it would be nice to hear your opinions, and I think I will take up. I will pause for half a minute after raising all these questions. So the first question is building a device research? Maybe you build a laptop, you bring components, maybe you assemble a phone, maybe you do something, physical entity, you build a device. Is that research? The question is building a new device research? That's the next question. Is writing a software research? You have all these advertisements of a certain company saying that, some red hat junior and will teach you how to develop apps, and then they show pictures of 6-year olds and 7-year olds developing their apps. Are they doing research when they write a software? When you write a software, are you doing research? Is writing a new software, is that research? That's one question that, again, for every question we will have some such counter question. Is repairing a device or debugging a software research? Maybe you are implementing some program and you find out errors in it and you debug it and make it work. Is that research? Or maybe you're repairing a device, maybe your vehicle, your car or your two-wheeler is not working properly. You take it to a mechanic and the mechanic fixes it. Is the mechanic doing research there? Is drawing a conclusion from a lot of data, is that research? Is proving a theorem research? Is formulating a theorem research? So I have all these questions and I would like to pause here for a while, and I sincerely hope some of you would understand
Is research to me. I think of, finding out all information about something. Now, for some people, that information might be known. For
yes,
some, it might not be known. So
yes.
when somebody finds out information for the first time, I would consider that research in true sense. And when somebody finds out information that already exists, that is also another form of research, I would say.
This is a very nice answer, although I disagree with it. But this is a very nice answer, and the distinction that you are making is very, very important. We will get back to this. But I'm happy that you tried to say something. The important point is research could involve any of the above or none of the above. All of these can be done without doing any research, or for that matter, each one of them may involve some research. So then what is research? These are just examples. So here is my working definition of research, and each and every word here, each and every adjective here, each and every noun here is very, very important for me. Okay. So this says research is a game of creating ideas that are significant. First of all, research is a game. It's a game that researchers play. And when we play a game, sometimes we win, sometimes we lose. Research doesn't necessarily mean that every time you set out to do something, you will succeed in doing it. But research also means that it's a game that you play. Whether you succeed or not, you will enjoy. You don't, obviously, no one likes losing a game, and one feels bad after losing a game. But one still wants to play the next game, not just because one hopes to win, but because there is some fun in this game. So that's the first thing of research. Research is a game that gives a lot of fun to people. That's the first point. Second point, research is a game. What kind of a game it is? It's a game of creating ideas. The two parts of this. First of all, it's a game of ideas. It's not a game of building device, as you know, some articles or some books or some talks may have you believe. It's not a game of developing new technology. New technology, new device is a consequence of this game. At the core of all of it is an idea. Even when you are when you're building a device, you have an idea, and it's the idea that you're playing with. Even when you're doing experimental research, when you're, let's say, working in your chemistry laboratory, you don't arbitrarily mix things. You have an idea, if I mix this with this, or if I heat up this up to this temperature, or if I do this, this should happen. You have a certain speculation. So all experiments are a way of speculating or finding out whether the speculated ideas make sense or not. All games are a way of generating observations that can lead to further ideas. So research is a game of ideas. It's a game of ideas. Now when I say it's a game of ideas, it's not a game of understanding existing ideas, it's a game of creating ideas. So there are great ideas given in some book, and I read that book, and then I say I'm doing research because now I'm playing the game of understanding those ideas. No, those ideas are already known. When we work with known ideas, we are essentially not doing research. We're doing research only when we create new ideas. So coming back to the distinction made by this girl, I'm sorry, I don't know her name. She said, I am looking at some information that someone else may have, but I don't have. Unfortunately, if someone else has that information and you don't have, you're doing research for yourself, but as far as the world is concerned, it will not be considered research. You are merely learning new things. Maybe you are rediscovering. That could happen. But whenever you are creating ideas, whether it's a rediscovery or reinvention or whatever else, you are kind of doing research. So research is a game of creating ideas. Now, is it is creating any kind of idea research? Any arbitrary idea would not qualify as research. That idea has to be innovative, and that idea has to be significant. So these are the important characteristics of the game of ideas that we play when we do research. So let's not worry about creation versus invention versus discovery. Let's not worry about that. But it's about creation of ideas and not execution of ideas. It's not about action. It's about reflection. It's about coming up with thinking and coming up with ideas. Of course, you might have to do experiments and validate the ideas. You may have to generate observations, etc. You may have to build device to show that idea works or whatever. But it's still at the core, it still amounts to creating ideas. Innovation is something very, very important part of research, and the significance could lie in the beauty of the ideas, in the utility of ideas, or in the enhancement of knowledge. So all these are important ingredients of research. So when I say research, the most important takeaway from this slide is research is a game of creating innovative ideas, creation of significant and innovative ideas. That's the thing that I want you to hold in your mind when we talk about research. Okay. So we have to answer a question: what is an idea? Research is a game of ideas. So what constitutes an idea? So an idea is not an isolated thing in a vacuum. It has a context, and the context often decides its significance. An idea is like a missing piece in a jigsaw puzzle. And I mean, if you know a certain, for example, you open up your book and you look at a question. Yes, you have, that this is a question and this is the answer. But someone tells you that this is a question that's going to appear in the exam tomorrow. Is the same question, is the same knowledge, but suddenly it becomes very, very significant for you. So it's the context in which an idea is made, that context decides its significance. Idea on its own may be thoroughly useless. So discovery of an idea completes some part of the puzzle. So you have some kind of a jigsaw puzzle and then there's something missing and you suddenly get an idea and you are able to fit something there. That is so that the remaining pieces that are already there, they are the ones which decide how important this idea is. They provide the context. Okay, an idea is a connection between other ideas. The more unlikely the connection, more beautiful the idea is. And I gave you that example of a question in your book. I mean, you have 200 questions. So, which question will appear in the exam, or will your professor create a new question for your exam? You don't know. But if somebody gives you a question and say, this is the question that's going to come in the exam tomorrow, it suddenly assumes a lot of significance to you. Sometimes we know what the puzzle would look like before getting the ideas. Some other time the picture emerges as we start discovering the ideas. Okay, so this is not sponsored by a mobile service provider which doesn't exist anymore. So we talk about ingredients of good research. So the important ingredients of good research are innovation, aesthetics, and there are other important aspects: completeness, rigor, empirical demonstration, effective communication. You ought to be able to show that your idea makes sense in practice. You ought to be able to communicate your idea to people. You ought to be able to ensure that they are able to see what your ideas are. So let's go over each one of them one by one. So assume that this is the sphere of knowledge, and initially you start learning something. This is sphere of your knowledge. You are learning something. So that red dot shows how much you know, and learning increases with time. Okay, and then after you finish your school, you go to your college, you start focusing and specializing. You say, okay, maybe I don't like biology so much, I like computer science. So maybe I'll do computer science, or maybe I'll go to medicine. You begin focusing and specializing. So this is the sphere of the knowledge, and red region is what is your knowledge. You specialize more and more until you reach the unknown. And when you reach the unknown, uh, so long as you are within this sphere, there is some book, some person, some research paper, some literature that would have an answer to your question. But then as you specialize more and more, you reach the unknown. You start asking a question, and suddenly now there is a different situation. And the situation is, so until now you've been asking questions, and there will be someone who will answer the question, or there'll be someone who will point you to this Google page or this page on the internet, and that would have your answer. But suddenly you reach a situation when you ask questions, and now there is no one to answer that question. And in that situation, you try to push the boundary. You realize that no one has the answer. So let me try and find the answer. You make an attempt to push the boundary. If you keep trying hard enough, you might succeed. So you might be able to create a small, tiny bubble on this sphere of the knowledge. Okay, when this happens, this is where you have brought in some innovation at the level of ideas. It's important for you to keep in mind that your view of the knowledge would be like this, that you have made created a big bubble, but the reality is that it's something very small. So this is innovation. Answering a question that someone could not have answered before. Coming up with a theory, coming up with an explanation that answers some questions that could not be answered before. Doing something which enables doing something that could not have been done before. That is where the innovation is. So everything that is new need not be innovative. For example, let's say you find sum of two obscure 100-digit numbers. Now, it's very likely that no one in this world has ever bothered to find the sum of these 200-digit numbers. So, in that sense, this is new. But is this innovative? No, this is not innovative. Creation without creativity does not qualify as innovation, because we already know how to find sum of numbers, even if they are 100-digit numbers or 1,000-digit numbers. If you ask me to find sum of two-digit numbers, it may take me a little longer, but I will be able to find the sum of two-digit numbers. So this is not novel. This does not bring the novelty quotient in research. The novelty quotient of an innovation depends on how non-obvious the result seemed before you establish it, and how obvious the result appears in hindsight. So if you were to do something that could not have been done before, then it is innovation. And it is highly novel if it seemed very hard before you did it, and after you did it, it seems, oh yes, of course, this is the way it should be. So that is what makes research novel. Innovation in research should enrich the set of first principles. So we always work with a set of first principles which we apply in order to draw various conclusions. So when we get a new first principle, that is research. And we will see several examples of this. Let's come to aesthetics. So when we talk about aesthetics, my favorite quotation here is that of Henri Poincaré. He said, the French mathematician Henri Poincaré, he said that a scientist studies science not because it is useful, but because it is beautiful. Here I do not talk about the beauty of appearance or beauty of qualities. Here I talk about that profound beauty which comes from a harmonious order of parts. And this is something very, very important. In order to illustrate this, my favorite example is that of a painting. Some time ago, I requested you to imagine that you are a sculptor. Let me now request you to imagine that you are a painter. Let's say you are a fan of MF Hussain, who is no more with us. But let's say you want to recreate one of his paintings. So you pick up a painting and you like the painting and you set out to recreate. But at the core, you are a student of science. You have done labs in the experiment, and you have your own precision measurement instruments with you. And your teachers have given you a good habit of noting down all the observations. So you look at the painting, you pick up your instruments, measuring instruments, and then you open up your register and start noting down certain things. What do you note down? You note down the area of the canvas, 30 centimeters by 20 centimeters. You note down in your notebook 30 centimeters by 20 centimeters. Then you carefully measure the part of the canvas that is colored in red. And you observe that it occupies 20% of the canvas. So you note down in your notebook 20% area red. And then you look at the color blue and you find that color blue occupies maybe another 20%. You note down color blue 20%. And then you see color green and you say color green, oh, this is beautiful. The 30% of the canvas occupies color green. You note down green 30%. Like this, you note down all colors. Okay. And now you set out to recreate the painting. And what do? You keep the painting away, you push it aside, you take another canvas which is 30 centimeters by 20 centimeters, you open up your notebook. You had noted that the color red occupies 20% of the area. So you mark out a corner on the canvas that occupies 20% and paint it red. Then you have noted that color blue occupies another 20% of the area. You find out another area which is 20% of the canvas, you paint it blue. And you noted that color green occupies 30% of the area, so you make another area which occupies 30% of the canvas, and you paint it green. And like this, you have maintained the proportions of all the colors as per your notings. And yet it is obvious that this is nowhere close to the original painting. Why? What is missing? What is missing in this case is the relative arrangement of the colors, the way various parts dovetail with each other. So this is that beauty that comes from a harmonious order of parts. If you mix those areas in a specific way, then it gives you that painting. If you mix them in some other way, that harmonious order is lost, and therefore it doesn't have the same aesthetic appeal as the original painting. What has to do with the aesthetic and the beauty of an idea? So let me take this simple example, and let me ask a simple question. What proportion of the box does the pink triangle occupy? That's the question. I mean, you could say 20%, you could say 30%, 45%, 52%, 60%, 49.5%, 70%, any answer. Give me the answer in percentage. Would anyone like to hazard a guess?
Sir, around say 70%, 70 to 75%.
70 to 75%. Okay. Any other answer? Everyone goes with what he said, 70 to 75%, or does someone have a different opinion?
Sir, in the chat box, we are getting 50 to 60%, 66%, 50%, so on.
Okay. 50 to 60, 66%. Okay. Let's try to answer this question. And this answer illustrates application of the first principles. Okay. So let me give you an idea. Okay. Let me give an idea of drawing a vertical line. Okay. Now that's not a great idea on its own. I mean, if you go out and tell that we had that professor from IIT Bombay and who taught us how to draw a vertical line, people will say, "Oh, what's the big deal about it? What's great about it?" So let's draw a vertical line, but we choose a specific spot. We draw a vertical line like this. This divides the rectangle into two parts. Would anyone like to revise their answer now? Someone please unmute or write it on the chat, and Niharika will tell me what you're writing on the chat.
Sir, now the answer is 50%.
50%. Now the answer is 50%.
Yes.
The answer is obvious, right? As soon as we drew this line, the answer became obvious. There are two rectangles now, and we have these lines in the rectangles that are the diagonals. They join the two opposite corners of a rectangle, and there is exactly as much area in each rectangle in the pink part as there is in green part. So both the areas better be equal. So they are identical. So it's 50%. That's the answer. Can't be 49.5%. No 66%. No 60 to 70%. It's exactly 50%. And we have arrived the answer by applying an idea from the first principles. What that means is when you fix an idea, several things get fixed. As soon as we decided to draw this vertical line here, you immediately got the idea that this area must be same as this area must be same as this area. So fixing of one idea often fixes many ideas. Ideas talk back to us. When we get the right idea, they tell us something much more than what we had imagined before. In this example, we didn't imagine it's exactly 50%. But as soon as we saw, okay, let's draw a vertical line, we immediately Now realize that yes, it better be 50%. It cannot be anything else. And that is where your formula half base into altitude comes from. Okay, so I will leave you with this question. What about this pink triangle? And I won't answer this, but please work it out. Okay. So what is the point that I'm trying to make? Ideas talk back to us. When we fix an idea, it fixes some other ideas. The beauty of ideas lies in creating simple and small number of ideas that bring in unexpected implications, that relate the seemingly unrelated things, that illuminate and reveal much more than anticipated. On their own, that particular idea, if you take it out of context, it's of no meaning. You say, oh, I know how to draw a vertical line, it has no meaning. But when you drew that vertical line in that box, then it got a lot of meaning. This is the meaning of total being greater than the sum of the parts. Okay? Let me stretch this idea a little more. The question is, what is the sum of all internal angles of a polygon? Okay? The first polygon, it's easy, 180 degrees. We all know that. For the second polygon, it's 360 degrees. For the third polygon, it's a pentagon, 540 degrees. Next, we have a hexagon. It's 720 degrees. So this is what we have learned. Now I throw another question at you. What is the sum of all internal angles of this polygon that has n sides? Does anyone know the answer? Quickly, 10 seconds, not waiting too much. I'm saying that there are n sides. Can you tell me what is the...
So someone has answered 90 into n, 810 degrees, and 9 minus 1 into 12.
Okay, good attempt. Let us try to answer this question. Again, I want to illustrate the meaning of answering from the first principles. Let me give you again a very simple idea that on its own doesn't mean anything. But as soon as you choose that idea, suddenly the answer comes in front of you. And the idea is to choose a certain point, arbitrary point, inner point, and connect it to all the vertices. That's the idea. Pick up an arbitrary point inside of the polygon and connect it to all the vertices. Now what happens? There are n sides. So there are n rectangles, right? The sum of internal angles of each rectangle is 180 degrees. So the sum of all angles of all these rectangles must be equal to n into 180. However, we need to remove this internal angle. That's very easy. It's 360 degrees. No matter how many rectangles that we have. And therefore, our formula is simple. N into 180 minus 360. That's the answer. Right? We don't have to remember the formula. See, just picking up that one idea, as soon as we picked up the idea of a vertex inside of the polygon, all other ideas got fixed. So this is an example of what I mean by beautiful ideas. These are still not research because they're not innovative, they're known to others. But I'm just showing you what we mean by the beauty of an idea. Okay, let's talk about rigor. Rigor removes imprecision and adds concreteness. It makes an idea immune to personal interpretation. Example, divide 6 by 2. Now you might say, why am I even asking this question? But there is a reason why I'm asking this question. So the question is divide 6 by 2 and obviously you will quickly say, okay, the answer is 3. But no, I don't want the answer. I want to know how did you arrive at the answer. I want you to give me a definition of what does it mean to divide 6 by 2. Let me suggest a definition, a possible definition, a possible explanation of getting answer 3 when we divide 6 by 2. A possible explanation is divide 6 into 2 parts and tell me the size of each part. So if you divide 6 into 2 parts, the size of each part is 3. So this is a possible explanation of a division. I would pause here for 5 seconds and I would like to know, I would like you to type it in the chat box if you agree with me. Just say yes or no. And Niharika will tell me how many of you are agreeing with me. Yes, Niharika, do we have some answers?
Yes, sir. Till now, 2 people have said yes.
They have said yes. Is there anyone who said no?
Not yet, sir.
Not yet. Let's wait for 5 more seconds. Okay, let's go with it. Let's say these two people agree with me and we apply this division, we apply this definition of division, and now I ask you a different question. Divide 6 by half. So which means that divide 6 into half part and tell me the size. Half part of 6 is 3. So 6 divided half is equal to 3. How many of you agree with this? At least the people who agreed with the definition earlier should agree with me. They can't disagree now.
Sir, we're getting yeses from everyone.
Yeah.
So even 50% of 6 with will be that.
Yes, but the question is divide 6 by half.
Yes, sir.
6 divided by half, how much is it? What is the answer?
So 6 divided by half is not the same as 6 divided by 2.
But we agreed on this definition and this definition seems to be giving us the same answer. Right? So what is 6 divided by half? Have you been taught wrong arithmetic in our childhood?
Sir, the chat is saying 12.
Chat is saying 12. That's what we have been taught. But that doesn't, our definition doesn't apply there. The problem is not that the answer is not 12. The answer is 12. Let me assure you, you have been taught well. Don't worry about that. The problem is not with the answer. The problem is with the definition. This definition is not rigorous. This definition doesn't apply to all situations. It answers the question in one situation, but not in the other situation. In particular, it answers the question when the divisor is integral. It doesn't apply when the divisor is not integral. If the divisor is a real number or it's a fraction and not an integer, then it doesn't apply. Here is a more precise definition, more rigorous definition. Instead of saying divide 6 into 2 parts, we should say divide 6 into parts of size 2. Instead of 2 being the number of parts, we say 2 is the size of the parts. And then tell me the number of parts. Now, when you say divide 6 into parts of size 2, the number of parts is 3. And now when you say divide 6 into parts of size half, tell me the number of parts. You take half, 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 and you're going to get 12 parts. And then you can heave a sigh of relief that yes, we were taught well. But the point is, when we write something like this, it has to be rigorous. And in science, it's very important for us to make a statement that is rigorous. Just because the statement looks correct on some examples doesn't mean that it takes care of all situations. Rigor removes imprecision. Okay, so I will go over this part relatively much more quickly. I will I would recommend you to read this book called Where Good Ideas Come From by Stephen Johnson. I'll take some examples, but I'll not spend too much of time. So the idea is that we have, when we want to create good ideas, there is a basis of good ideas, there is a domain of good ideas where we expect to find ideas, and there are heuristics of exploring the ideas, and there are ways of facilitating the good ideas, and we will see some examples without spending too much of time. So what is basis? Basis is available technologies, resources, ideas, things that are already known. And the domain is what is called adjacent possible. This is a very, very important term. Adjacent possible is the the knowledge that has not been explored yet, but from the first order linear combinations of the things that are known, you may be able to arrive at those things, although you may not know what to combine and how to combine, right? So basis is mature ideas, mature technologies. These are the things that we already know. And the idea is that there are flexible connections between these things. You try to create many more connections, you allow free flow of ideas, and suddenly by doing this, you find something that lies outside of this. So this is where you're playing with the basis, and suddenly you get an idea which is outside of the basis. That is in adjacent possible. So whatever is outside the boundary of the knowledge lies in adjacent possible. You know, this adjacent possible is the area that is adjacent to the boundary of knowledge. You're likely to find an idea that is closer to the boundary. What that means is you are extending the boundary. So this boundary defines the limit. And now you have new boundaries. So ideas that were not known earlier now become known, and now you once again start playing the game to create ideas, good ideas that are outside of the known ideas. So this adjacent possible is a term coined by Stuart Kaufman in 1995. So here is the basic principle behind it is that boundaries grow as we explore them. For example, you are inside a new place, you are inside a new room in a new building. You don't know what lies behind a certain door. Maybe you came from one door, but there's another door. You don't know what lies behind it. Maybe there is a wall, maybe there's a balcony, maybe there is a staircase. You don't know, or maybe there is some other room. You find a new door and open it, and now you have a better idea what that place is. But there's another room. You have to open the other room. So what is behind the door is adjacent possible. It may lead to yet another door that needs to be opened. And a nice idea of adjacent possible and a nice idea of extending the boundaries, a nice analogy is that your car headlights or your two-wheeler headlights provide only a short look ahead at night, and yet you can cover the long distance over time, because as your vehicle moves forward, other area get lit. So you, although you are unable to look at only a fixed distance, that the place that you're looking at keeps changing, your boundaries keep growing, you're bringing more and more adjacent possible into the existing knowledge, and that's how you can make the travel even in the night. Okay, here are some heuristics which I am really not going into the details. I mean, this talk will need another 1 hour if I were to talk about this heuristics. These slides are available on my homepage. You can feel free to look up my slides, and feel free to send me an email if you have questions about this. But essentially, you try to see duality, you try to see symmetry, you try to generalize by removing specificities, you try to distill the idea to an essence, you try to extend an idea, you try to adapt idea in an unknown concept. We will look at some of these examples here. So, for example, Charles Babbage, all of us have heard here as the father of computer science. His analytical engine was far ahead of its time. The basic ideas were in place in 1837. The design was far too complex for the available technology. At that time, the technology was mechanical gears and switches. So he had the design of a computer, but the computer could not be made with the existing mechanical gears and switches, which means that his idea at that time was not in the adjacent possible, it was non-adjacent. However, he also designed something called a difference engine, which led to the calculator, which was well within the bounds of adjacent possible. It was a, believe me, first calculator was a 15-ton contraption with 25,000 mechanical parts. Okay. After many involvement, the idea actually became in adjacent possible when William Burroughs started the mass production in 1844. All of us know, I don't know how many of you heard of Fortran, but Fortran was the first programming language. That's the programming language with which the compilers came into existence. At that time, people thought that, it's better to write programs. You cannot write program in a higher level language. You need to write program only in assembly language. Okay, but John Backus said that there is an imbalance between programming cost and computer cost. There's a technical difficulty in writing specifications that are expressive, and the main obstacle was, you observe, that clumsy treatment of loops and array address calculations. So he came up with the idea, and he made an important observation. He was an example of a right person at the right time at the right place. He had the foresight to recognize that efficient language implementation was well within the adjacent possible. Okay. So adaptation is an example of using an idea in a completely unrelated context, leading to cross-fertilization of ideas. So first example of adaptation is this: screw press was used for wine making. So Gutenberg saw that screw press where, they would turn a screw and thereby will be able to press grapes to create wine. He took that idea and applied that to printing press because everything else was ready. The movable typeface using lead fonts was ready, the ink was ready, the paper was ready, types were hand pressed, and the process was slow and not suitable for mass production. So Gutenberg essentially invented a machine that used screw press, whereby you can press the types on paper quickly, and that brought out the printing and allowed mass printing. Adaptation example 2 is French weaver Jacquard's punch card system. Punch card system was used for weaving, but it was used by Charles Babbage for representing programs. Uh, this is an interesting idea, and I'm going to spend about a minute on this. So adaptation example 3. So these were the two students. So at that time, this is 1957, there was a competition between USA and Russia. It was USSR at that time, United Socialist Republic. So, so they had released Sputnik, the satellite, in the orbit. So in the applied physics laboratory of Johns Hopkins University, Guer and Wenbach created this tracing system for this. The idea was that Soviets very proudly said this satellite is orbiting around the earth, and as soon as it comes to your place, you will hear a certain frequency emitted by the satellite, and that's the proof that we have released a satellite in the sky. So these two people essentially created a system which will receive the frequency, amplify, and they were able to record when the satellite moved around that area, and whenever the satellite would come closer, because of the Doppler effect, they will be able to hear a bigger sound. And then they started collecting people around it, and they said, okay, after some observation, they said after 1.5 hours you will hear this big sound, and the people would gather after 1.5 hours, and they will hear a big sound, and they'll say, okay, let's come back and hear once again after 1.5 hour, I'm sorry, to hear the sound. So what had they done? They had essentially said that here is an object that is emitting a frequency, here is a receiver. Based on the amplitude of the sound that we are getting, the base of the amplitude of the wave that we are getting, we can predict the distance. And based on the way this amplitude is changing, we can predict the position. We can say, when does this object come here? When does this object come closer to it? So inverse of this idea was used for deciding the trajectory of missiles fired from a submarine. So this system was the origin of the modern day GPS system. Our phone is the receiver and satellite is what is essentially transmitting signals, and we receive it, and then we are able to know, we get from the satellite, we have a map and we get the information from the satellite, and we know where we are standing, and that's the modern day GPS system. And the adaptation example number 4, which is Shannon's master's thesis. This is the most celebrated thesis in the world so far, master's thesis in the world so far. It was called the symbolic analysis of relay and switching circuits. I'll tell you in a minute why it's the most important master's thesis. He essentially observed that switches were either open or closed. He did use or made this observation in 1937, and he used Boolean algebra. He coincided nicely with the algebra created by George Boole in 1847. So Boolean algebra was invented 90 years before it was actually applied for reasoning about electrical circuits. When Shannon created this thesis, suddenly design of electrical circuits became an engineering, it became a science rather than an art. And that is what led to creation of computers. All modern computers, all computing is based on the things that Shannon did in his master's thesis in 1937. So it's one of the most important and most influential master's thesis. Let me skip the rest of the things. There are many examples here. Let me not, there's this serendipity and various things. Let me just skip that in the interest of the time. Let me come to the process of research. Okay. My high school teacher used to emphasize on me this thing, which I understood much later. He used to say that very few of us know how much we have to know in order to know how little we know. This might look like a play of words, but it's not really just a play of words. Imagine this is the sphere of your knowledge, not the knowledge of the entire world. And you know everything that is inside of the sphere, and you don't know anything that is outside of the sphere. Your measure of your ignorance is proportional to the surface area of the sphere. You know everything that is in the sphere, you don't know anything that is outside of the sphere. And therefore you say that I don't know things, and how many things I don't know, that is decided by the surface area of the sphere. Now, if you acquire more knowledge, what happens? If you acquire more knowledge, your sphere becomes bigger. The area of the sphere becomes bigger. It means that you now know things that you didn't know before. Earlier, you thought there are only so many things that I don't know. But when the sphere becomes larger, you now know more things and say, okay, I don't know this as well, I don't know this as well, I don't know this as well. So your measure of ignorance increases in proportion to the knowledge that you acquire. The more knowledge you acquire, the more you realize that the less you know. And therefore, very few of us know how much we have to know in order to know how little we know. Why is this relevant for research? There's something called relative stupidity versus productive stupidity. What is relative stupidity? Relative stupidity is where your teachers or your parents tell you he got 90 marks in mathematics and you got 60 marks, you're stupid. You're relatively more stupid compared to that person because he knows mathematics more than that. Relative stupidity is comparing ignorance of two people. But there's something called productive stupidity, which says that everyone is stupid at some absolute level. We're taught to feel bad about relative stupidity. We're taught to feel bad about our ignorance. And productive stupidity, on the other hand, says we should celebrate our ignorance because until we celebrate our ignorance, we cannot overcome it and find out new knowledge. No research is possible unless we are willing to feel vulnerable and stupid. When we do research, we often feel stupid, but that is productive stupidity. We feel stupid saying, oh, we don't have an answer to that question. But we know that no one else has answer to that question as well. So that is also stupidity, but that is productive stupidity because that leads us to producing something. We are able to do research. Most people are unable to do research because they can't see this ignorance as productive stupidity. They see this ignorance as relative stupidity. In fact, when you're doing research, if you're not feeling stupid, I can guarantee you that you're not doing a serious research. You will do a serious research. Whenever you do a serious research, you will continue to feel stupid. Many people give up research because they can't stand this feeling of stupidity. So it's important to know what we know and what we don't and be comfortable with it. So let me skip some questions. Let me skip this breadth versus depth. Let me skip this slide in the interest of the time, not very important. I want to talk about the most important slides. Uh, yeah. Research is a journey from confusion to conviction. So there is a starting point. How does research happen? So you say, I want to answer this particular question. And then you say, I will be able to answer this question if I can. You divide that question into smaller parts. You say, I'll be able to answer this question if I can answer these 5 questions. You started off with one question and now you have 6 questions. And then you pick up each one of them and divide it in further sub questions. Okay. So you started off with one question and now you have a bag of 100 questions. Your confusion grows. You were happy not knowing answer to one question. Now you have 100 questions whose answers you don't know. Okay. But at the same time, two things happen. What are the two things that happen? A, each question starts becoming smaller and smaller. Its granularity becomes smaller. B, your mind starts making connection between the questions. And then with those 100 questions, you're able to say, okay, these 5 questions are irrelevant. Maybe I can throw them away. And then you say, these 10 questions are much more easily answered. This is the answer to these questions. So now from 100 you down to 85. Like this, you either eliminate the questions or you answer the questions and your conviction grows, and that's how you reach the answer. Very often people give up on research because they don't know when the growing conviction or when the growing confusion will lead to growing conviction. We have to have that patience and keep generating more and more questions, and we will find the answer. It's very important for us to raise the right questions. If we do not raise the right questions, we will never reach the answer. This slide is the most important slide according to me in this set of slides. Research can be characterized. This, in fact, this, instead of talking about research, let me talk about this curve as something that's applicable to everything. On the x-axis, you have time or effort. On the y-axis, we're plotting quality or maturity or gains that we have. What this means is initially you have to put in a lot of effort in order to get some gains, and after a while, with relatively little effort, you get many more gains, and then once again the law of diminishing returns starts taking shape. This is a very polymorphic curve. You can apply it to anything. You can apply it to your learning. You can apply it to your career, you can apply it to your friendships, you can apply it to your relationships. Essentially says that anything can be divided into three broad regions. In the initial region, you have to work hard. What does this region tell us about research? Research life cycle also follows the same curve. And based on where you are on this curve, and it's very important for you to ask yourself where you are on this curve in your research life cycle. When you are in this part of the curve, you have to tell yourself something. When you are in this part of the curve, you do something else. When you are in this part of the curve, you do something else. So when you are on this part of the curve, you have to tell yourself that look, I am merely starting. I cannot expect to see quick rewards. I need to put in more time. I need to put in more effort. I cannot afford to get frustrated. I cannot expect to get answers right away. This is an investment. I should not try to see returns right now. Returns may be small, but I should not worry about it. So this is a time for me to bring in all my persistence, all my motivation, all my tenacity, all my perseverance. I must persevere. I should not give up. This is what we tell when we are in this region of the curve. When we are in this region of the curve, we should tell ourselves, okay, my time has come. Now I am in a productive zone. It would be very stupid of me to give up now, because this is the time of reaping the rewards of the hard work that I have done in past. This is a time when I must put all my energy together. This is a time when I must bring my focus together. This is a time when I should not digress. This is a time when I should not give up the initiative that I have got, the tempo that I have got, because this is when I'm going to get lot of benefits by putting in small efforts. That's what we tell us when we move from this part to this part. The important question is, how do we know that we have crossed this knee? That's a hard question, but my experience tells me one thing, and this experience, my all my colleagues and all my students agree with this experience. As soon as you cross this knee, you suddenly find that the world has changed. You suddenly find that the world is green all over. You find nice cool breeze all over. People who used to frown at you until yesterday start giving you the most radiant smile. You hear birds singing all around you. And whenever that happens, you should tell yourself, okay, I have reached this part in research, in my research life cycle. And when you cross over this knee, the law of diminishing returns starts taking shape. And what do you do in such a situation? In such a situation, you do what I do: go out to different places, give talks on your research, tell people what research you are doing, and try to find some other problem on which you are in this region for that particular problem. The difficulty is that when we this productive zone, there are pitfalls in hitting this productive zone. Okay, initially when we are in the honeymoon period, our confidence or interest is very high. Okay, our confidence, we pick up all the books, we put up an alarm at 6 o'clock in the morning, get up in the morning. From today I'm going to study very hard, and we study very hard. After some days we keep scratching head, and after some time our confidence droops. Okay, it just dips. Okay, we have to persist here. We get into a valley, and coming out of this valley is where all the persistence and all the effort is needed. Okay, so we have to keep trying. Even if our confidence goes down, even if our interest goes down, we have to keep trying, and then we will hit the zone where we will, after which we will expect to see better things. Of course, in reality, the curve may look like this. You might one day feel very high, the next day you will feel very low. The third day, some of your friend tells you, let's do it together, and you feel high, and then you get bored the next day. So that's how things will happen. An important question that often gets asked to me is the difference in research in industry versus research in academia. I'll spend a little bit of time here, not too much of time. The most important thing is research in industry is driven by a product, whereas research in academia is driven by ideas. A product is typically based on a large number of ideas. So research in industry needs to combine the results of many idea driven research efforts, faces the challenge of deployment of idea much more significantly than that of creating ideas, must work with a series of well defined short term goals, and focusing on an independent idea may not be possible for a long time in industry. Whereas research in academia is typically not bound by a particular product. It can afford to focus on ideas exclusively for a very long time. It can work with ill-defined and long-term goals. It can afford to have longer gestation period. For example, I'm working on point analysis for about 12 years now, and I think I will have to work for another 5 years before which I can uh, get the answers to the kind that I'm looking for. The important point is deliverables exist in academia also, but are of a different nature, and deadlines are usually as strict as in industry. So let's come to the last part of the talk, and would this is the most important part of the talk, where I talk about some of the interesting statements made by Richard Hamming on research. This is the same Richard Hamming because of whom you have to study Hamming code, whether you like it or not. Okay, so on the role of luck, Pasteur had said that luck favors a prepared mind. Hamming says something very interesting. Our society frowns on people who set out to do really good work. You're not supposed to. Luck is supposed to descend on you and you do great things by chance. And then he goes on to say, well, that's kind of a dumb thing to say. I spoke earlier about planting acorns so that oaks will grow. You can't always know where to be, but you can keep active in places where something might happen. And the next statement is very, very important. It's one of the most, one of my favorite statements made by Hamming. He says a prepared mind sooner or later finds something important and does it. So yes, it is luck. The particular thing you do is luck, but that you do something is not a matter of luck. Whether you work in data science, whether you work in databases, whether you work in computer networks, whether you work in computer graphics, whether you work in compilers, that's a matter of luck. It's a matter of luck depending upon the kind of people there are around you, depending upon the kind of teachers that you get, depending upon the kind of researchers you talk to. So in which area you work, the particular thing that you do is luck. You're lucky that you have great people in a certain area, but the fact that you do something is not a matter of luck. You need to have a fire in the belly to do something. If you don't have that hunger, if you don't have that fire, no matter how many great people are around you, you will not do any research. So yes, it is luck that you do something in a certain area on a certain topic, but doing great work is not a matter of luck. It's a matter of hard work. Luck is when preparation meets the opportunity. Through hard work, we must prepare ourselves, and then the opportunity might open up in front of us in terms of the people we might meet, or in terms of the ideas that come our way. Okay, so Richard Hamming was the in charge of computer division in Bell Laboratories. This is, I'm talking about situation that existed 70 years ago. So about 1950s, Fortran was not created yet. So it was just the Second World War was getting over, and people were wanted more and more. Scientists wanted more and more programs to be written, and they had a series. They had a collection of programmers who would write these programs. At that time, when they wrote programs in assembly language. and there was a bigger demand. So he walked up to the management saying that I need more people to write programs because programming is becoming important, and management flatly refused. But Richard Hamming didn't give up. Richard Hamming was a believer of power of machines. Richard Hamming tells himself this. Look at what he says to himself. Hamming, you think the machines can do practically everything. Why can't you make them write programs? Why do we have to write programs for the machines? Why can't machines write programs? This was called automatic programming. This appeared as a defect to him initially, but he started thinking of automatic programming. It was called automatic programming by him at that point of time. Now it's called high level languages. So, by a change of viewpoint, what appears to be fault often turns out to be one of the greatest assets that you can have. So, if computers require low level languages to program, we can use the power of the computers so that we can program them in higher level languages. That's the shift of perspective. Just imagine if Richard Hamming and some other people who initiated that had not thought about it. Today we would have no Zoom. Today we would have no computer science. Today I would not be sitting in my office and sharing all these ideas with you. We don't even know how the world would have been. This simple question that because I believe machines can do everything, why should I have to struggle with the machines? Why can't machines simplify my work? That led to this beautiful practical application of computers in terms of programming. Okay? Doing research is a test in which you are allowed to write your own question paper and answer it. You're free to use the question, and you get often marks not just for the answer but how important the question is. And once you know the right questions, you will find the answer. The answers will fall in place. Often we don't get answers because we don't know what are the right questions to ask. And then you've heard of this before several times. Research is 1% perspiration and 1% inspiration and 99% perspiration. Newton had said if others would think as hard as I did, they would get similar results. And Hamming says something that's the most favorite statement of mine. The gist is that continuous consolidation works like a compound interest. Hamming says, given two people of approximately the same ability and one person who works 10% more than the other, the latter will more than twice outproduce the former. So what it's trying to say is, supposing you are used to working for a certain amount of time, let's say 5 hours, 6 hours every day. Let's say you decide to work for half an hour extra every day. Just half an hour, not much. At the end of 1 month, you have put in 15 hours of extra effort. On the 31st day, when you put in that half an hour is not half an hour. It's much more than that, thanks to the continuous consolidation that you have done before. Its effect is equivalent to several hours. If you keep putting that extra half an hour on a regular basis, when you put in half an hour at some point of time, you will be able to get worth something 10 hours in that half an hour. Here is a simple thing. If we increase our work by 1% every day, 1.01 raised to 365, or we reduce it by 1%, that's a compounding effect. It's not just a question of actual effort or actual time. It's the effective effort, it's the effective time. If we do not put in, if we try to put in less effort than yesterday, and we keep doing that every day, you will be surprised by the factor. In the first case, the answer is hard to guess. The answer is 38.161. So you become that much more effective. you have a multiplication factor in your effectivity by 38. Whereas if you were to just reduce it by 1%, you will find that you are nearly zero. If you lose the initiative, you lost everything. You can't be doing research, you can't be doing great work. Okay, so the physical time remains same, but you're able to give deep attention to ideas with small conscious effort. You must have uh, heard of these terms called getting into the zone or getting into the flow. Okay, so consolidation through hard work helps you to reduce your conscious effort. You're preparing your mind to do better work with every effort that you put in. The most important thing is the difference between ordinary and extraordinary is that little extra that is put in before the ordinary. Okay, and in order to get that extra, we need to have the initiative to find what is that extra. It must be smart and relevant extra, not arbitrary extra. We have to use controlled imagination. We need to have patience and discipline to keep doing that extra again and again. This initiative, this patience and this discipline helps you to get in the zone. And then the role of intelligence and courage in research. So Hamming says, how about having lots of brains? Says it sounds good, but great work is something else than mere brains. So he says one of the characteristics you see, and many people have it, including great scientists, is that usually when they were young, they had independent thoughts and had the courage to pursue them. Once you get your courage up and believe that you can do important problems, you can. If you think you can't, almost surely you're not going to. That is a characteristic of great scientists. They have courage. They will go forward under incredible circumstances. They think and continue to think. And now there's another important point on the role of drive and commitment in research. So, what separates people who are very productive from people who are not very productive? Well, he says, well, one of the reasons is drive and commitment. The people who do great work with less ability but who are committed to it get more done, and those who have great skill than those who have great skill and dabble in it, who work during the day, go home and do other things and come back and work the next day. They don't have the deep commitment that is apparently necessary for real first class work. Now, why is this important? And this is again a very, very important point that he says. So he says if you're deeply immersed and committed to a topic, day after day, your subconscious mind has nothing to do but to work on your problems. And so you wake up one morning or on some afternoon and there is the answer. That's how people discover answers in dreams, or just walking, looking at the sky, you suddenly get an answer. Okay, for those who don't get committed to their current problem, the subconscious goofs off on all other things and doesn't produce a big result. So how should you become creative? It's very important. Don't let anything else get the center of your attention. You keep your thoughts on the problem. Keep your subconscious starved so it has to work on your problem. It has nothing else to do. Keep your subconscious starved so it has to work on your problem so you can sleep peacefully and get the answer in the morning free. That is how we become creative in research. And then on the role of uncertainty, most people like to believe that something is or is not true. Great scientists tolerate ambiguity very well. They believe the theory enough to go ahead, they doubt it enough to notice the errors and faults so that they can step forward and create the new replacement theory. If you believe too much, you'll never notice the flaws. If you doubt too much, you won't get started. It requires a lovely balance. But most great scientists are well aware of why their theories are true, and they're also aware of some slight misfits which don't quite fit, and they don't forget. So, coming to three requirements of creativity, you have to have deep knowledge. You have to keep your antennas tuned. You never know when and where the signals will come from. You have to be able to hold a problem in the background, thinking for a long time without acting on it. Your subconscious mind should be able to work on it. We ought to be able to deal with loosely structured ideas and structure them over time. Okay, and now this is another interesting thing. Most scientists know many important problems. They have something between 10 and 20 important problems for which they are looking for an attack, and when they see a new idea come up, one hears them say, well, that bears on this problem. The great scientists, when an opportunity opens up, get after it and they pursue it. What is the meaning of an opportunity opening up? The meaning of an opportunity opening up is recognizing that we have crossed that knee on the S curve and we got into the productive zone. When that happens, they drop all other things, they get rid of other things and they get after an idea because they had already thought the thing through. Their minds are prepared, they see the opportunity and then they go after it. So that's what Richard Hamming said. Let me just conclude my talk by summarizing the most important things that I said. In a rapidly changing world, quick self learning is the most important ability. It is enhanced significantly by exposure to research, and research experience is likely to become more and more important in future. So, what is the essence of research? Research is a game of innovative ideas, game of creating innovative ideas that are significant. Even an experimental research begins with an observation and a speculation, and the significance of ideas could lie in any of the following: beauty, utility, or enhancement of knowledge. Research is often a cycle of speculate something, design an experiment, design an argument, design a proof, apply, perform experiment, apply the idea, observe uh, the behavior, interpret the observation, infer something out of it, and repeat the whole thing. So that is what is research. Ingredients of good research are innovation, aesthetics, and completeness, rigor, effective communication. What does it take to be a researcher? Well, what we may already possess: motivation, curiosity, perseverance, good grasp. These are the things that can't be taught. You learn these things by osmosis. You learn these things by being in company of the people who are motivated, who are curious, who are creative, who persevere, and who are very bright. But we may have to acquire some things with effort, a strong background, which enhances the effectiveness of all these, particularly when time is a crucial factor. So, to be or not to be, that is the question. For me, the answer stops at the first bullet. Research is fun. It's fun to play this game. There can be no better fun than playing with ideas. But then there are valid answers. Research makes researcher a much better learner. Research enables better consolidation of skills. Coming back to this, why do people do research? That's the question that we had asked. Okay. This is similar to the question, why do mountaineers climb mountains? Okay. Do they climb mountains to get money? Obviously not. They often have to arrange for loans or they have to look for sponsors. They put in money from their own pocket. So certainly it's not money. Do they do it for fame? What kind of a fame? When you climb a mountain, there is no one else at the top clapping for you. So clearly not for fame. Do they do it for power? Do you feel more powerful? Do you feel more secure when you're sitting on top of Mount Everest? So none of these answers apply. But the reply given by a mountaineer was, why do mountaineers climb mountains? Because mountains exist. A researcher solves problems because problems exist. Money, fame, power, security, solving problems, everything else is secondary. Research is a test of mental and physical endurance. And the real reward is an unforgettable experience of nature in its purest form for a mountaineer and for a researcher. It's an unforgettable experience of knowledge and creation of knowledge, of ideas in its purest form. Research is a test of intellectual agility and endurance. Research is driven by passion, and research takes us to a very different state of mind. The cause of passion may be different, there may be personal goals, there may be philanthropic goals, and let me just skip them. There are lots of valid reasons why you may want to do research. You may want to seek intellectual fun, you may want to create wealth, you may want to create knowledge, you may want to solve the problem, you may want to create opportunities for others, you may want to change perceptions of the people. So, how is research different from problem solving? It comes back to a remark by that girl in the beginning. When we solve intellectually challenging problems, it also requires creativity, perseverance, intellectual endurance, etc. It also creates a good learning experience. The difference is that the questions addressed may not be new, may be new to the person, but not to some others. Research addresses questions that have not been addressed before or have not been addressed adequately before. Okay? So, here are quick 10 commandments on research. Adapt, seek extension to an earlier known problem. If you have a solution, find a problem. Let slow hunch simmer in your mind. Find out the right questions to ask. Seek generality by removing specificities. Seek symmetry by testing for dualities. Distill the essence by distinguishing the relevant from the irrelevant. Learn to believe and doubt ideas at the same time. Build levels of abstractions and migrate between them. Mix up deep thinking with routine mechanical work so that your subconscious works on the things and the conscious mind is busy. 10 commandments of success in research: work on important problems, work on multiple problems. For each problem, identify where you are on the S curve, seek excellence and beauty in your work, get emotionally involved with the process, not with the results. Judge your day by the seeds you sow and not by the harvest you reap. Remain committed, work hard, work continuously, consolidate your understanding, don't depend on luck, handle uncertainty and disappointments. That is the question that was asked to me. What is the biggest challenge in research? The biggest challenge is to handle uncertainty and handle disappointments. But if you look at these carefully, you observe that these are not something very different from what we have to face anyway. These are required in any intellectual pursuit. These are applicable to a practicing engineer, a student, a teacher, and all intellectual pursuits. So that's all that I have to share about research, and I will be happy to take questions. Feel free to unmute yourself or open up the chat. I can also try to see the chat.
The chat box is open for responses or questions that you have. Please feel free to put your questions there.
Okay, everyone believes 6 divided by half is 12. I'm glad. Someone says, no, no, it can't be 3. I'm happy. Yeah, please feel free to ask questions.
So, so could you please give us some motivation, some tips on how not to lose motivation while working on a research paper? Because like you said, we will face hurdles and difficulties and the curve will drop at
Yes,
times.
yes, yes, that will happen. So, what is the question? How not to use motivation? Meaning, I didn't get it.
So yeah, how tips on how not to lose motivation.
How
So that
not to
we
lose? Oh, I'm sorry. I heard how not to use, and I was wondering
can.
how not to lose motivation.
Yes.
You have to be excited about the work that you do. Passion and excitement. You have to be passionate about it. All people who do great work not because it solves the problem. Of course, that's one of the reasons. But this passion is something very important. If you are not excited enough about what you're doing, if you're not passionate about what you're doing, I mean, I can't teach you how to be passionate, but when you start doing something for some time and you start looking at some beautiful aspects, then you have to make a commitment that you have to tell yourself, I am passionate about it, and no matter what, I'm going to do it. That passion and that excitement has to come in. I mean, often people who do PhD, often people who do research, at some point of time, it becomes a question of their existence. They say, look, my existence doesn't mean anything if I can't do it. That's the way you have to push yourself. If you can't push yourself that way, you will lose motivation, you will give up. Because in research, success cannot be measured by the time that you have put in, the number of papers that you have read, the number of papers that you have published, the amount of money that you have made, how famous you are, how well people know you. None of these things is helpful. What is helpful is a fire in the belly, a deep desire. I have to do it. If you do research for getting marks, yes, you will be able to do something. You might even be able to do something useful. Okay. But it will not be what I would like to call a great research. It will be useful, it will teach you something, it will expose you to something, but in order for not to lose passion, not to lose motivation, that can happen only through, that cannot happen through external factors. It has to happen through internal factors. I don't know if I have answered your question. The other way of not losing motivation is to be in touch with the people who are excited about the problems that you're trying to solve. Be in touch with the people. You will find they are extremely passionate, they are very motivated, and then you will see small things that they do in order to remain motivated. How they work hard, how they ignore certain things, how they say no to various things, how they guard their time very well, how they manage their time. These are the things that you have to learn by osmosis. Have I answered your question?
Yes, I think I understood the part that I need to find.
Yeah. So,
So we
Ek-
have more
yeah,
questions also.
yeah. So Ekta says, what are
Yes.
some specific journals related to IT for publishing research papers? Ekta, it depends on the area, on the topic on which you wish to work. The number of journals in IT easily runs in thousands, and I'm serious about it, maybe even tens of thousands. Take my word, if there are 1,000 journals, take my word, at least 950 of them are junk, absolute junk. There is something called predatory publishing. You type it in Google and you will come across predatory publishing. You will have electronic journals, they'll call themselves International Journal of such and such a thing. You submit a paper on Monday, they'll give you an acceptance on Tuesday, and then they'll say submit fees on Wednesday, and then your paper will be published on Thursday. This is a commercial bargain. This is an academic fraud. Unfortunately, it's not a financial fraud as yet recognized by the government of India. So it's still not illegal, but it's an academic fraud because they have no value. So you, the best way to find good journals is to talk to the people who are working in the area of your interest. Find out what people are doing, where people are publishing, read up the papers, and that will give you some idea. Of course, there's a lot of hard work. I don't mean to say that all this can be done in a day or two. So I have a talk, a set of slides on my homepage. The second part of this talk, which deals with how to write a good paper. You can go through it, and there are some questions. There is also a talk on uh, uh, PhD. what are the issues in doing PhD, you might find answers to some of your questions there. Venkatesh wants to know what to do if you have found an area of interest but are not technically very sound in that area. How do you move forward in such a situation? Venkatesh, the best thing to do is to get in touch with experts in that area and ask them what is it that you need to do in order to develop your background. Trust me, every researcher, every expert in that field will be more than willing to give a hearing ear to you, provided you show a genuine interest. The trouble is we keep receiving hundreds of emails and most of the emails are very casual. People want to know something because they are 50 marks in their course, and therefore, I ignore all such emails. I give them some homework, I try to see what work they are doing, and then I spend a lot of time with them. So get in touch with the people who are working in that area. How do you find people working in that area? Go to the web pages of the institutes, go to IIT Bombay computer science web page, look at the people, what they are doing. You have to be able to convincingly tell them that yours is a genuine case. You tell them what you have done, you should read up what they have done, ask them questions about what they have done, then they will get interested. Otherwise, all of us keep receiving dozens of emails, if not every day, maybe every alternate day, every week, and uh, we have developed a knack of ignoring the emails that seem casual. I hope it answers your question. In most of the questions, at the core of it, my answer will be get in touch with the experts in that area. Okay. Any other question?
So,
Yeah.
sir, if there is anything innovative if we get, and there aren't much any ideas regarding, even if we search in the internet, we don't get much ideas what we should do in that situation.
Same answer. Get in touch with the experts.
Okay.
Find out experts in that area.
Okay, sir.
Experts would have an idea of what's happening. I mean, you want to work in data science, machine learning. We have some of my colleagues are world-renowned experts in that area. Try to look up what they are doing. Tell them what you have done. Be very specific about the question that you are answering. You have to sell yourself to them, but you have to get in touch with the experts. There is no substitute to getting in touch with the experts. Beyond a certain point, you can't learn from books, you can't learn from internet, you can't, of course you can find a lot of information, but validation of all that information has to come from internet, because internet has a tremendous power to fool you and to mislead you. I hope none of you feel that I'm hand waving or avoiding answering your questions. I'm trying to give you a very blunt answer. It may be not a very pleasant answer, but that's the reality. If you have a question, get in touch with me through email. And if I do find a genuine email, I'll be very happy to answer the email.
Sir, I believe these all questions were the last of them.
Yes.
And
so thank you very much to all of you for listening to me so patiently. I know it's a very long time. You're used to a 1 hour lecture, but I have engaged you for much longer than that. So thank you very much.
yes, sir. Sir, thank you so much for giving us such an informative session. And Chahana?
Yeah, so I would once again like to invite Mr. Wilson Rao sir onto our virtual stage to share his thoughts with us.
I think we have a mixture of audience over here, sir, wherein I'd like to tell that mainly the idea was for the MSc students who have been there, started their kind of research in the area of data science or big data and all those things. But having said that, they were facing little difficulties how to start about the research. And obviously the questions when asked, where the technical, details we are finding out, but aggregating these details into the area in which we are trying, they are trying to research on, it's a big kind of decision, basically. Yes. And a lot of work has to happen. So I've given some, kind of feeder that you will get little kind of help. And with all these kind of lectures, we are trying to get experts in those areas where they can have a talk. First, I wanted them to understand how the research has to be started and how, you have done beautifully that how patients and how getting the ideas and how to group in these ideas, and having to know how to get the success in that. It's a bigger kind of issue. So I hope every student over here have understood that getting a research is just not a one-day effort where we will be putting and tomorrow there will be some result out of it. Like we get certain times some projects from some students. At the last we get automatically some project coming out before the exams. So the same thing goes for the TY. That's how you need to work for your even projects, even your applications which you make. And even our SY students we have invited because we have kept in our syllabus, sir, SY as a year of research where they can start in SY itself what projects and what technologies they want to do. And so that is how even the SYs are over here. So you have to take this, session very seriously, students, and make sure you learn that the correct aspects of starting, how to take an idea and how to get success from that idea. And don't just get bogged down that I'm not having any kind of technical know-how. You need to strive to get that thing. Until unless you don't have an interest, the opposite person won't have interest. So you need to actually get in touch with people like sir has said and show them your interest so that they can go all the way out to help you out. If you just do it for the sake of, nothing can work. So thank you, sir, for inspiring the young minds and guiding them in all these things. We also hope you to come regularly and have a check whether this session has been fruitful for them. And I believe that everyone over here would start a serious kind of work now onwards. And not even just you all, everyone in MSc too. And we will get certain kind of results so that next time sir comes, so we will be able to give him the feedback that how we started and what motivation we got it from today's session. So thank you once again, sir. And we look forward for such kind of sessions from you. And thank you for the valuable time, sir. And thank you, everyone. Okay. And please, put it in practice what you learned now. Just don't hear and just leave it. Put it in practice and see that it will definitely yield you results. So thank you and God bless. Bye.
Thank you very much. Goodbye.
Thank you, sir. Thank you.
So once again, I would like to thank Dr. Uday Khetkar, sir, for coming and sharing his experience today. It is a delight to have you here, sir.
Thank you.
And I would also like to thank Mr. Wilson Rao, sir, the head of our department, for giving us the opportunity to attend such enlightening sessions.
Thank you both.
Thank you, sir.
Thank you, sir.
I hope everyone enjoyed today's session. I would like everyone to please look in the chat box. You will find the feedback form over there. Please fill it in for securing our AAA credit points. Thank you, everyone.
Thank you.
Okay, bye.
Thank you, sir.
Bye.
Bye.
Sir.
Bye, sir.